Long before the first human voice echoed through a forest, before the rise of mammals and the familiar continents we know today, the Earth was a different world. A single colossal landmass, Pangaea, baked under a hotter sun. This was the Mesozoic era, an age spanning over 180 million years. It was an epoch of giants, a time when life experimented with forms both alien and awe-inspiring. This was the reign of the reptiles. But within this sprawling empire of scales, one dynasty was destined to become legendary. They began small, scurrying in the shadows of larger, more established reptilian predators during the late Triassic period. They were a new breed, distinguished by a subtle but profound evolutionary innovation in their hips, allowing their legs to be positioned directly beneath their bodies. This upright stance granted them greater speed and agility than their sprawling-limbed cousins. From these humble beginnings, they would rise to dominate every terrestrial ecosystem on the planet. They were the dinosaurs, the terrible lizards, whose story is one of unparalleled success, diversification, and eventual catastrophe. But their legacy is not just one of size and power on the ground. It is also a story of conquest, of a journey that would take them into the last great unconquered realm, the sky. For much of the Mesozoic, however, the skies were not ruled by dinosaurs. They belonged to another group of extraordinary reptiles, the Pterosaurs. It is a common misconception that these creatures were flying dinosaurs. They were not. Pterosaurs were a distinct branch of the reptile family tree, the first vertebrates to evolve powered flight. Their anatomy was a marvel of biological engineering. Their wings were not formed of feathers, but of a leathery membrane of skin and muscle called a patagium. This membrane stretched from a dramatically elongated fourth finger all the way to their ankles. From the petite insect-eating Anurognathus to the colossal Quetzalcoatlus, with a wingspan rivaling that of a small airplane, Pterosaurs diversified into a stunning array of forms. They soared over primeval oceans, plucking fish from the surface with long, tooth-filled beaks. They stalked the ground on all fours, folding their wings neatly at their sides. They were masters of the air, a successful and long-lived dynasty that held dominion over the heavens for over 150 million years. Their existence proves that the drive to conquer the sky was a powerful evolutionary force, one that would arise independently in different lineages. But their method of flight was unique, a path that dinosaurs themselves would not follow. So, if a pterosaur isn't a dinosaur, what is? The distinction, crucial to understanding this ancient world, lies hidden within the skeleton. Paleontologists define dinosaurs by a specific set of anatomical features, the most important being a hole in the hip socket and a unique femoral head that fits into it. This arrangement, known as a perforate acetabulum, created that pillar-erect stance, with the legs held straight under the body. This posture was more efficient for moving and breathing and supported far greater weight than the sprawling gait of crocodiles or lizards. This key adaptation was the foundation of their success, allowing them to grow to sizes unmatched by any other land animals in Earth's history. It enabled the nimble bird-like movements of the raptors and the ground-shaking locomotive power of the giant sauropods. When we imagine a dinosaur, we instinctively picture this upright posture. We see a triceratops charging, its powerful legs driving it forward, or a herd of hadrosaurs migrating across a floodplain, their bodies held high off the ground. This fundamental body plan separated them from all other reptiles of their time and set them on a unique evolutionary trajectory, one that would lead to astonishing diversity and, for one special lineage, a revolutionary new way of life. On the ground, the dinosaur dynasty flourished, splitting into two great clans based on the very hip structure that defined them. First were the Saurischia, the lizard-hipped dinosaurs. This group included the long-necked sauropods, gentle giants like Diplodocus and Brachiosaurus that browsed the tops of ancient forests, their immense bulk supported by those pillar-like legs. It also included the theropods, the bipedal carnivores that ranged from crow-sized hunters to the formidable Tyrannosaurus rex. Their story is one of predation and an evolutionary arms race that shaped Mesozoic ecosystems. The second great clan was the Ornithischia, the bird-hipped dinosaurs. Ironically, the group less closely related to modern birds. This diverse assembly included the armored ankylosaurs, walking fortresses covered in bony plates. The horned ceratopsians like Triceratops, with their elaborate frills and formidable horns for defense and display. And the great herds of duck-billed hadrosaurs, whose complex dental batteries allowed them to grind tough plant material. For tens of millions of years, these two clans diversified, filling every conceivable terrestrial niche. They were the undisputed rulers of the land, giants and dwarves, hunters and hunted, shaping the world beneath their feet. But all this time, the sky above remained the domain of the Pterosaurs, a vast open frontier that seemed beyond their reach. Why did the sky remain unconquered by dinosaurs for so long? The answer may lie in their own success. The evolutionary path that led to the towering sauropods and the powerful tyrannosaurs was a commitment to terrestrial life. Their skeletons became heavier and more robust to support massive weight. Their bodies were engines built for power on the ground, not for the delicate and demanding physics of flight. For a dinosaur to take to the air, it would require a radical departure from the successful body plan of its ancestors. It would need to become smaller, lighter, and more specialized. It would need to find an evolutionary pathway, a series of gradual changes that could transform a creature built for walking and running into one capable of defying gravity. What catalyst could possibly drive such a transformation? Was it the pursuit of new food sources, like flying insects? Was it a way to escape the ever-present danger of larger predators on the forest floor? Or was it for mobility, a way to move through complex, three-dimensional environments, like dense forests? The question of how flight began is one of paleology's most compelling mysteries. The answer wouldn't be found among the giants, but in a small, unassuming branch of the theropod family tree, where a revolution was quietly beginning. The first clue to this aerial revolution was not a wing, but a feather. For decades, feathers were thought to be a defining characteristic of birds, evolving specifically for the purpose of flight. But remarkable fossil discoveries, particularly from the rich deposits of Liaoning, China, have completely rewritten this story. We now know that feathers are a deeply ancient feature of dinosaurs, appearing long before any of them could fly. The earliest feathers, found on small theropods like Sinosauropteryx, were not the complex aerodynamic structures we see on modern birds. They were simple, hair-like filaments, more like downy fluff than flight feathers. What was their purpose? Almost certainly, their primary function was insulation. For small, active dinosaurs, a coat of primitive feathers would have been essential for regulating body temperature, much like fur on a mammal. As they evolved, feathers became more complex and colorful. On dinosaurs like Archaeopteryx, they formed elaborate fans on the tail and arms. These were likely used for display, to attract mates or intimidate rivals, painting the Mesozoic world in colors we can only begin to imagine. The feather, an icon of flight, began its evolutionary journey as a prehistoric blanket and a billboard. Its co-option for flight would come much later, a perfect example of evolution repurposing an existing structure for a brilliant new function. With lightweight bodies and a covering of increasingly complex feathers, the stage was set for the final leap. But how was it made? Two main hypotheses compete to explain this pivotal moment. The trees down, or arboreal theory, suggests that small feathered dinosaurs took to the trees, perhaps to escape predators or find food. From there, they began by leaping from branch to branch, then gliding, using their feathered limbs to control their descent. Over generations, this gliding could have evolved into powered, flapping flight. The opposing ground-up or cursorial theory argues that flight began on the ground. Fast-running dinosaurs may have used their feathered arms for balance while chasing prey or running from danger. These small, wing-assisted leaps and flaps could have provided extra thrust and lift, eventually leading to sustained flight. Fossils provide tantalizing clues for both theories. The four-winged dinosaur, Microraptor, with long flight feathers on both its arms and legs, seems perfectly suited for an arboreal, gliding lifestyle. Meanwhile, the iconic Archaeopteryx, perhaps the most famous transitional fossil of all, possessed a blend of features: the feathered wings of a bird, but also the toothed jaw, clawed fingers, and long, bony tail of a dinosaur. It was a creature of two worlds, living proof that birds are not just related to dinosaurs, they are dinosaurs. This feathered branch of the theropod family tree survived the extinction event that wiped out their giant relatives, carrying the dinosaur legacy through the age of mammals and into the present day. The terrible lizards never truly vanished. They simply learned to fly. For over a century, our image of the dinosaur was set in stone and in popular culture. They were titans of a bygone era, magnificent but fundamentally alien, scaly, cold-blooded reptiles destined for extinction. The groundbreaking fossil of Archaeopteryx in the 1860s provided a tantalizing link to modern birds, but it was largely viewed as a singular, evolutionary oddity. The great chasm between bird and dinosaur seemed vast and unbridgeable. But in the 1990s, deep within the hills of northeastern China's Liaoning province, paleontologists began to unearth a fossil treasure trove unlike any other. Ancient lake beds, buried in successive layers of fine volcanic ash, had created a prehistoric Pompeii. This unique geology preserved not just bone, but the delicate, ghostly impressions of soft tissues, skin, organs, and something that would fundamentally rewrite the story of life on Earth. A revolution was stirring, buried in the silent rock, waiting for the right moment to reveal a lost world of feathered dinosaurs. The first true tremor of this revolution came in 1996 with a small, unassuming fossil. Named Sinosauropteryx prima, or first Chinese dragon feather, it was a compsognathid, a type of small, agile theropod. To the naked eye, it looked like a perfect skeleton. But under careful preparation and analysis, a breathtaking secret was revealed. Surrounding the bones, from head to tail, was a halo of dark, fibrous material. These were not scales. They were simple, hair-like filaments, a primitive form of feather we now call proto-feathers. The scientific world was electrified and deeply divided. Skeptics argued they might be degraded collagen fibers from the skin, but meticulous study after study confirmed their feather-like nature. Even more astonishingly, microscopic examination of preserved pigment cells, or melanosomes, allowed scientists to reconstruct its coloration. Sinosauropteryx wasn't just fuzzy, it sported a bright, ringed tail of reddish-brown and white bands. For the first time, we weren't just looking at the bones of a dinosaur. We were seeing a living, breathing, vibrantly colored animal. Sinosauropteryx was not an anomaly. It was the vanguard. The Liaoning fossil beds began to yield a spectacular and ever-growing diversity of feathered dinosaurs, proving that proto-feathers were not a one-off experiment. Creatures like Archaeopteryx and Archaeopteryx, relatives of the more famous Oviraptor, took the next evolutionary step. They possessed complex veined feathers on their short arms and fanning out from the tips of their tails. These were structurally similar to modern bird feathers, with a central shaft and interlocking barbs. Yet, these animals were clearly flightless runners. Their arm feathers were too short and symmetrical to generate lift. So what was their purpose? The evidence points overwhelmingly towards display. Like a peacock's tail or a bird of paradise's plume, these elaborate feathers were likely used in courtship rituals, for species recognition, and to intimidate rivals. They were billboards advertising health and fitness. Before feathers were for flight, they were for communication. And they also served a vital secondary role as an insulating layer, trapping body heat and fueling the active, warm-blooded metabolism that we now believe most theropods possessed. The journey from display structures to aerodynamic surfaces is one of evolution's most elegant stories, and the Liaoning fossils provide the most crucial chapters. Among the most stunning of these is Microraptor, a small dromaeosaur, or raptor, that pushed the boundaries of what a dinosaur could be. Discovered in the early 2000s, Microraptor presented an anatomical configuration seen nowhere else in nature. It had feathers not just on its arms, but also on its legs, forming a bizarre but effective four-winged arrangement. And these were not simple filaments or symmetrical display feathers. They were long, modern-looking, and distinctly asymmetrical, with a shorter leading edge and a longer trailing edge. This asymmetry is the key hallmark of a true flight feather, essential for creating an airfoil and generating aerodynamic lift. How it flew is still a subject of intense scientific debate. Was it a passive glider, launching from trees, or could it achieve a form of powered flight? Whatever the method, Microraptor proves that nature was experimenting with flight in multiple fascinating ways. And thanks to melanosome analysis, we know it did so cloaked in glossy, iridescent black feathers, shimmering like a modern-day raven. The feather revolution was not limited to the small and agile. For years, it was assumed that as theropods grew larger, they would have shed any insulating coat to avoid overheating, much like modern elephants are largely hairless compared to their woolly mammoth ancestors. This idea was dramatically overturned in 2012 with the announcement of Yutyrannus huali, the beautiful feathered tyrant. This colossal animal was an early relative of Tyrannosaurus rex, stretching nearly 30 feet long and weighing well over a ton. And it was covered from snout to tail in a thick coat of long, shaggy filamentous feathers. 3 beautifully preserved specimens confirmed this wasn't an isolated feature. The discovery was a watershed moment. It proved that even giant apex predators could be fluffy. Yutyrannus lived in a cooler period of the early Cretaceous, where its thick, downy coat would have been essential for insulation, keeping its massive body warm. It completely reshaped our vision of the great predatory dinosaurs, replacing the monstrous, scaly depiction with a far more awesome and scientifically accurate image of a feathered titan, a true king of its cool, forested domain. For a time, feathers seemed to be an exclusive innovation of the theropods, the lineage of carnivorous dinosaurs that includes birds. But the fossil beds of China held yet another surprise, one that threatened to rewrite the very base of the dinosaur family tree. The discovery was of Tianyulong, a small two-legged plant-eater. It belonged to a group called the Ornithischians, or bird-hipped dinosaurs, a branch that split from the theropods very early in their history. Astonishingly, running down Tianyulong's back was a row of long, stiff, bristle-like filaments. These structures, while simple, are considered homologous to the protofeathers of theropods. This finding was profound. It suggested that feathers weren't just a theropod invention. What if the common ancestor of all dinosaurs was itself covered in some form of fuzzy integument? This idea is bolstered by evidence from their close relatives, the Pterosaurs, the flying reptiles of the Mesozoic, which were covered in their own insulating filaments called pycnofibers. The picture that emerges is one where fuzz was the default, and the scaly skin of giants like Triceratops or Brachiosaurus was a later, secondary adaptation, not the primitive state we once assumed. The fossils of Liaoning province have, in the space of a few decades, completely redrawn our vision of the Mesozoic. They have filled in the evolutionary gaps with astonishing clarity, transforming a once linear path to flight into a complex and bushy tree of experimentation. The world of the dinosaurs was not a drab, gray, and green landscape populated by scaly monsters. It was a world buzzing with vibrant color, intricate behaviors, and a stunning variety of feathered forms. From the ginger-striped tail of Sinosauropteryx to the iridescent wings of Microraptor and the shaggy coat of Yutyrannus, we now see these animals as they truly were: dynamic, warm-blooded, and deeply connected to the birds that fly in our skies today. The clear, sharp line that once separated bird from dinosaur has been irrevocably and beautifully blurred. The feathered revolution revealed that the age of reptiles was, in fact, an age of feathered dragons, a reign far more magnificent and stranger than we had ever dared to imagine. The great forests of the early Cretaceous were a vertical world, a three-dimensional maze of giant conifers, cycads, and ferns. For the smaller inhabitants, life was a constant negotiation with gravity. Moving from one canopy to another meant a perilous journey down to the forest floor, a realm stalked by much larger predators. But evolution is a master innovator, and in these dense ecosystems, a remarkable solution was taking shape. It wasn't about conquering the ground, but escaping it altogether. This was the dawn of gliding, a controlled fall that transformed a dangerous descent into an efficient, life-saving mode of transport. For a select group of small feathered dinosaurs, the dromaeosaurids, the air was becoming a new frontier. They were pushing the boundaries of what it meant to be a dinosaur, using their evolving plumage not just for warmth or display, but to ride the currents of the air, to leap from the heights and drift through the silent, misty spaces between the giants of the plant kingdom. This was the first, crucial step towards the sky. Among these early aerial pioneers, one creature stands out as a testament to evolution's elegant and sometimes strange solutions: Microraptor Gi. Discovered in the rich fossil beds of Liaoning, China, this crow-sized carnivore was a revelation. It wasn't just its beautifully preserved feathers that captivated scientists, but their arrangement. Microraptor possessed long, asymmetrical flight feathers not only on its arms, but also on its legs, making it a true four-winged dinosaur. The glossy, black iridescence of these feathers, revealed by fossilized melanosomes, suggests they may have also played a role in communication or display. For years, paleontologists have debated how it used this unique anatomy. Did it hold its legs beneath its body, creating a biplane-like configuration for stability and lift? Or did it trail them behind, using them as a rudder or for pitch control? Whatever the precise method, Microraptor was a masterful glider, an arboreal hunter that could silently swoop down on its prey, small mammals, lizards, and fish, from the canopy above, a feathered phantom of the Cretaceous forests. Gliding, for all its elegance, is a passive act. It is the art of falling with style, a surrender to gravity, albeit a controlled one. True, powered flight is an entirely different proposition. It is an active rebellion against gravity. It requires an engine. This evolutionary leap from drifting to flapping demanded a radical redesign of the dinosaurian body plan. The primary challenge was generating immense power. This meant developing massive pectoral muscles, far larger than any needed for simply grasping or climbing. And these muscles needed a solid anchor point. The solution was the evolution of a deep, keeled sternum, or breastbone, a feature absent in Microraptor but fundamental to all flying birds today. Furthermore, the shoulder joint had to be re-engineered to allow for the complex rotational motion of a powerful upstroke, a motion that would actively generate lift and thrust. Without these anatomical innovations, the dream of sustained, powered flight would have remained forever out of reach, tethered to the highest branch. The engine for flight is muscle, but the surface that harnesses the air is the feather. Feathers did not, however, evolve for flight. Their story begins much earlier, likely as simple hair-like filaments providing insulation for small, warm-blooded dinosaurs. Over millions of years, these structures grew more complex, branching out and developing into the intricate forms we see in the fossil record, likely used for species recognition and courtship displays. But for flight, one specific adaptation was paramount: asymmetry. A flight feather is an aerodynamic marvel. Its leading edge, the side that cuts into the wind, has a shorter, stiffer vane. The trailing edge is longer and more flexible. When air flows over this shape, it creates a pressure differential: lower pressure above, higher pressure below, resulting in lift. This simple principle, encoded in the structure of a single feather, is what allows a bird to fly. This transformation of a simple filament into a sophisticated airfoil was the key that unlocked the sky, turning a tool for warmth into a wing for flight. How did these feathered dinosaurs make the final leap? Paleontology's great debate on the origin of flight has centered on two competing ideas: trees down versus ground up. The arboreal, or trees down hypothesis seems intuitive. It suggests that creatures like Microraptor, already living in trees, became accomplished gliders first. From there, they could have gradually added small, tentative flaps to extend their glides, control their descent, or soften their landings. Over generations, these flaps would become stronger and more coordinated, eventually evolving into true powered flight. Conversely, the cursorial, or ground-up, hypothesis argues for a terrestrial origin. It pictures small, fast-running dinosaurs using their feathered forelimbs for other purposes. Perhaps they were used for balance during high-speed pursuits, or as nets to bat down insect prey. A more recent variation suggests they used their wings for wing-assisted incline running, flapping to gain more traction while running up steep slopes or trees. In this model, the flight stroke evolved on the ground, a tool for agility that was later co-opted for the air. Bridging the gap between glider and flyer is one of the most famous fossils ever discovered, Archaeopteryx. Found in the Jurassic limestones of Germany, Archaeopteryx is the quintessential transitional form. It had a toothed snout, a long bony tail, and claws on its fingers, all primitive traits inherited from its theropod dinosaur ancestors. Yet it also possessed fully modern, asymmetrical flight feathers, arranged on well-developed wings, and a fused clavicle, or wishbone, features intrinsically linked with avian flight. So, could it fly? All evidence says yes, but probably not like a modern bird. Its skeleton lacks the large, keeled sternum needed for a powerful, continuous flight engine. Archaeopteryx was likely a weak flyer, perhaps using powered, flapping flight in short bursts to escape predators or move between trees. It was not a master of the air, not a soaring eagle or a swift falcon. It was a pioneer, an awkward but audacious first draft of the avian body plan, bravely flapping its way into a world no dinosaur had ever known. The leap was made. With the advent of powered flight in creatures like Archaeopteryx and its successors, a new dimension was opened for vertebrate life. The sky, once the exclusive domain of insects, was now a dinosaurian realm. This innovation triggered a spectacular evolutionary radiation. Throughout the Cretaceous period, the skies filled with an astonishing diversity of avian dinosaurs. Foremost among them were the enantiornithes, or opposite birds, named for their unique pattern of bone fusion. They were the most successful and widespread group of birds in the Mesozoic, ranging from sparrow-sized tree dwellers to gull-like shorebirds. They coexisted with their giant, non-avian relatives for tens of millions of years, diversifying into countless forms. The journey from a four-winged glider clinging to a branch to flocks of sophisticated flyers darkening the sky was a long and complex one. It was a process of trial and error, of anatomical refinement and behavioral adaptation that ultimately gave rise to the over 10,000 species of birds that grace our planet today. While the great dinosaurs laid claim to the continents, another group of reptiles conquered a different, vaster territory, the sky. These were the pterosaurs, the first vertebrates ever to achieve powered flight, an evolutionary leap of breathtaking audacity. It's a common misconception to call them flying dinosaurs. In truth, they were a distinct branch of the Archosaur family tree, cousins to the dinosaurs, not members of their direct lineage. For an astonishing 150 million years, from the late Triassic to the very end of the Cretaceous, they soared, swooped, and stalked across every continent, from the poles to the equator. Their dominion was absolute. Their defining feature was a revolutionary adaptation, a wing unlike any that had come before or has come since. It was not made of feathers, but of skin and muscle, a tough, flexible membrane called a patagium. This living sail stretched from the side of the body to the tip of a spectacularly elongated fourth finger. This unique anatomical blueprint launched a dynasty, allowing them to become the undisputed rulers of the Mesozoic skies. The pterosaur wing was an engineering marvel. The patagium was a complex, dynamic aerofoil, not a simple sheet of skin. It was laced with a network of stiff fibers called actinofibers, which prevented tearing and allowed the wing to be precisely shaped and stiffened during flight, much like the battens in a modern sail. This membrane wasn't naked hide. Exquisitely preserved fossils reveal that pterosaurs were covered in a dense, hair-like coat of filaments known as pycnofibers. These were not true feathers, but a unique covering that provided critical insulation. This, along with other anatomical clues, strongly suggests a warm-blooded, active metabolism was necessary to power their flight. Powering these incredible wings were enormous flight muscles anchored to a large keeled breastbone, or sternum. Their bones were hollow and pneumatic, connected to a sophisticated system of air sacs that both lightened their skeletons and enhanced their respiratory efficiency, a critical adaptation for sustained aerial activity. It was a complete biological flight system. The story of pterosaur flight begins in the late Triassic period, in a world recovering from a mass extinction. The earliest known forms, like Eudimorphodon, were relatively small, perhaps the size of a modern gull. They already possessed the fully formed wing structure, indicating an even earlier, undiscovered origin for the group. These pioneers had long, bony tails, often ending in a diamond-shaped vein that acted as a rudder for stability in the air. Their jaws were lined with sharp, multi-cusped teeth, perfectly suited for snatching insects on the wing or plucking small, slippery fish from the water's surface. As the world moved into the Jurassic period, pterosaurs began to diversify in the lush, warm climates. Creatures like Dimorphodon appeared, characterized by its large, deep, puffin-like skull and two distinct types of teeth in its jaws. These early flyers were crucial, establishing the foundational body plan that would, over millions of years, evolve into an astonishing array of species, each exquisitely adapted to a specific way of life in the skies of the Mesozoic. The sheer diversity of the pterosaurs is staggering, a testament to their evolutionary success in a world without avian competition. They occupied nearly every aerial niche imaginable. In the gloom of Jurassic forests, the tiny, bug-eyed Anurognathus, with its short, incredibly wide mouth, hunted insects at dusk, behaving much like a modern bat or nightjar. Far from these forests, along the shores of ancient lagoons, waded the bizarre Pterodostro. This pterosaur developed over 1,000 long, bristle-like teeth in its lower jaw, forming a perfect sieve to filter tiny crustaceans from the water, a lifestyle akin to a modern flamingo. In the skies above the oceans, crested pterosaurs like Tapejara and Tupuxuara sported enormous, elaborate head crests. These structures, likely covered in colorful skin, were not for flight dynamics, but for species recognition and attracting mates, filling the air with vibrant visual displays. From agile insect hunters to flamboyant giants, pterosaurs demonstrated that their unique wing was a gateway to a world of ecological opportunity. As the Cretaceous period reached its zenith, pterosaur evolution produced its ultimate titans, the Osdarchids. These were the largest flying creatures ever to exist. The most famous, Quetzalcoatlus, was an animal of mind-boggling scale. Standing on the ground, it was as tall as a giraffe, with a wingspan of over 10 meters, rivaling a small airplane. How did such a colossal animal get airborne? The answer lies in its unique anatomy. Unlike birds, which launch using their two legs, Osdarchids performed a quadrupedal launch. From a four-legged stance, they would vault into the air using the immense power of their folded wings as front limbs, a single explosive push that propelled them skyward. Once airborne, they were masters of soaring. But their life was not spent at sea. Their anatomy points to them being terrestrial stalkers, striding across prehistoric plains and wetlands like giant predatory storks. They were apex predators, using their immense, sharp beaks to hunt small dinosaurs and other terrestrial prey. While the pterosaurs commanded the skies, another group was beginning its own aerial ascent, the feathered dinosaurs. This set the stage for a tale of two wings, a fascinating example of convergent evolution for aerial dominance. The pterosaur relied on its membranous patagium, a single continuous surface stretched on one finger, generating powerful lift, ideal for efficient long-distance soaring. In contrast, creatures like Archaeopteryx and the ancestors of modern birds developed wings composed of a mosaic of individual, interlocking feathers. This innovation offered incredible damage resistance. A tear in one feather was not catastrophic, and allowed for finer control over the wing's shape for enhanced agility, particularly in cluttered environments like forests. This fundamental difference in wing design likely led to niche partitioning. Pterosaurs may have dominated the open skies and coastlines, while the smaller, more agile early birds thrived in wooded habitats. They were not always direct competitors, but rather two distinct and brilliant solutions to the immense challenge of conquering the air, each with its own strengths and weaknesses. For 150 million years, the skies of planet Earth belonged to the pterosaurs. From the smallest insect eaters to the gigantic Ashdarchids, they had diversified into a spectacular dynasty that witnessed the rise and fall of countless dinosaur species below. But their reign, like that of the non-avian dinosaurs, was brought to a sudden and cataclysmic end. The Chicxulub asteroid impact, 66 million years ago, plunged the world into a global winter, collapsing the food chains upon which they depended. The great pterosaurs, so exquisitely adapted to their world, vanished forever. They left behind no living descendants. Yet their legacy is immortalized in stone. Every fossil we unearth, from the delicate bones of their wing fingers to the faint impressions of their pycnofibers, tells a part of their story. The scientific process of discovery continues to reshape our understanding of these animals, revealing them not as simple reptiles, but as complex, dynamic, and successful creatures. They were the pioneers of vertebrate flight, and their silent, bony wings continue to inspire awe and teach us about the breathtaking possibilities of life. For over 150 million years, dinosaurs ruled the land. But a vast, unclaimed territory stretched above them, the sky. While the pterosaurs, cousins to the dinosaurs, had long mastered this domain, a new dynasty was stirring. On the forest floors and in the low branches, a revolutionary lineage of small carnivorous dinosaurs was undergoing a profound transformation. Their scales were giving way to a soft, insulating down, and then to complex, interlocking feathers. These feathers, initially for display or warmth, would become the key to unlocking the aerial world. This was not a sudden leap, but a gradual ascent, a story of evolutionary ambition written in bone and feather. It began with gliding from tree to tree, a controlled fall that slowly morphed into something more. It was the birth of powered flight, and with it the dawn of the avian dinosaurs. The most iconic pioneer of this new age is a creature that perfectly bridges two worlds. A feathered reptile, a clawed bird, the magnificent Archaeopteryx. Found preserved in the exquisite Solnhofen limestone of Germany, Archaeopteryx is a perfect evolutionary mosaic. It possessed a wishbone and flight feathers, hallmarks of a modern bird. Yet it retained the unmistakable signature of its theropod dinosaur ancestors, a mouth full of sharp carnivorous teeth, a flat sternum suggesting weaker flight muscles, and a long, rigid tail, vertebrae by vertebrae, unlike the fused tailbone of birds today. Its wings, too, held a primitive secret. 3 fully formed clawed fingers, ideal for gripping branches or perhaps even subduing small prey. For decades, paleontologists have debated its aerial prowess. Was it a powerful flyer or merely a sophisticated glider? The evidence suggests an intermediate stage. It likely engaged in short bursts of flapping flight, a kind of tree-to-tree aviation, allowing it to navigate the complex archipelago environment it called home. Here, among the warm, shallow lagoons, it would have hunted for insects, small lizards, and other creatures, a testament to life's remarkable ability to conquer new ecological frontiers, one flap at a time. As the Jurassic gave way to the Cretaceous, the skies came alive. The tentative experiments of Archaeopteryx gave rise to a new and wildly successful dynasty of avian dinosaurs, the Enantiorniths, or opposite birds. Their name derives from a subtle but crucial difference in their anatomy, the way the bones of their shoulder joint connected, which was the reverse of modern birds. This new arrangement, along with other skeletal modifications, made them stronger, more agile flyers than their predecessors. For nearly 80 million years, they were the undisputed masters of the air. They diversified into an astonishing array of forms and sizes, colonizing every continent on Earth. There were sparrow-sized insect eaters flitting through the undergrowth, shorebird-like probers wading in ancient wetlands, and even larger, more robust forms that took on the role of aerial predators. The opposite birds represented a massive evolutionary radiation, filling the skies with a complexity and diversity that rivaled the dinosaurs on the ground below. Nowhere is this Cretaceous aviary more vividly preserved than in the fossil beds of Liaoning, China. 120 million years ago, this was the Jehol biota, a world of deep lakes and active volcanoes. The fine-grained ash from frequent eruptions buried countless creatures, preserving them in breathtaking detail. Here we meet Confuciornis, one of the earliest known birds to possess a true toothless beak. It lived in great flocks, and the fossils reveal a fascinating detail. Males sported a pair of long, streamer-like tail feathers, likely used for courtship displays, while females lacked them. Flying alongside it were smaller, more nimble avians like Sinornis, a creature with a more advanced flight apparatus, capable of sustained flight and intricate maneuvers. This rich fossil record paints a picture of a bustling, competitive ecosystem. The air was thick with the calls and movements of dozens of different species, each carving out its own niche, from the high canopy to the water's edge, in a world dominated by feathered flight. While most avian dinosaurs conquered the air, some embarked on a different evolutionary journey, returning to the water. In the great western interior seaway that split North America in two lived Hesperornis. Reaching up to 6 feet in length, it was a formidable marine specialist, the Cretaceous equivalent of a cormorant or diving loon. Evolution had stripped it of flight entirely. Its wings were reduced to tiny, useless vestiges. Instead, all of its power was channeled into its hind limbs. Its legs were massive, its feet not webbed but equipped with wide, flattened lobes on the toes, perfect for propelling it through the water with incredible speed and agility. Hesperornis was a pursuit predator, chasing down fish in the shallow sea. Its long, slender snout was not a beak in the modern sense. It was a jaw armed with rows of small, needle-sharp teeth, canted backwards to ensure that any slippery fish it caught had no chance of escape. It was a master of its aquatic domain, a dinosaur that flew through the water. The Cretaceous seas and coastlines were rich hunting grounds, and they fostered the evolution of highly efficient aerial predators. Among the most successful was Ichthyornis, or the fish bird. Superficially, it bore a striking resemblance to a modern seagull or tern, with long, pointed wings and a powerful build indicative of a strong, dynamic flyer. It was a master of coastal soaring, riding the thermal updrafts along cliffs and scanning the waves below. But to mistake it for a modern bird would be a grave error. A closer look at its skull reveals its ancient predatory heritage. Like Hesperornis, its jaws were packed with dozens of tiny, sharp, recurved teeth. Ichthyornis was a widespread and dominant hunter, found from the Americas to Eurasia. It would have patrolled the coastlines in large flocks, a formidable presence, its piercing calls echoing over the water. It would dive with stunning precision, snatching fish and squid from the surface, a perfect fusion of a modern bird's body plan with the primitive weaponry of a theropod dinosaur. For tens of millions of years, this incredible diversity of avian dinosaurs filled the skies, the forests, and the seas. The fluttering of Archaeopteryx had given rise to a global empire of feathered creatures. From the opposite birds that dominated every continent to the specialized divers of the inland seas, they were an evolutionary triumph. But their long reign was about to come to an abrupt and violent end. 66 million years ago, a catastrophic asteroid impact plunged the world into darkness. The ecosystems collapsed, and the vast majority of life perished. The great non-avian dinosaurs vanished forever, and with them went almost all of the incredible avian lineages that had flourished throughout the Cretaceous. The skies fell silent. Yet life endures. In the shadow of this global cataclysm, a few small, resilient species managed to survive. They were the ancestors of the euornithes, the true birds. From these humble survivors, a new dynasty would rise from the ashes, repopulating the planet and giving flight to the 10,000 species of birds we know today. The feathered dragons were gone, but their legacy echoes in every birdsong. The late Cretaceous was a world of titans, the final, spectacular act in the dinosaurs' long reign. For over 150 million years, they had diversified into an astonishing array of forms, dominating every terrestrial ecosystem. Here, in the wetlands and forests of what would become North America, giants still walked the earth. The colossal Tyrannosaurus rex, an apex predator of bone-crushing power, hunted formidable prey like the three-horned Triceratops and the armored Ankylosaurus. Herds of duck-billed Edmontosaurus, numbering in the thousands, migrated across vast floodplains, their calls echoing through forests of cypress and sequoia. The skies belonged to the Pterosaurs, some with wingspans rivaling a modern fighter jet. Life was a complex, intricate dance of survival, honed by millions of years of evolution. The planet was a vibrant, thrumming greenhouse, a paradise for the giants who had inherited it. But this world, so stable and so ancient, was blissfully unaware. It was operating on borrowed time. High above the atmosphere, beyond the familiar moon, an interstellar traveler was closing a cosmic appointment, set in motion billions of years before. It was an asteroid, a city-sized remnant from the formation of our solar system. For eons, it had traveled a solitary path through the void, its trajectory eventually nudged by the gravitational pull of distant planets. Now it was captured by the sun's gravity, accelerating on a collision course with the third planet. Measuring nearly 10 kilometers in diameter, it moved at a speed almost impossible to comprehend, 20 kilometers per second, fast enough to cross the Atlantic Ocean in under 4 minutes. It was a silent messenger of destruction, carrying more energy than every nuclear weapon on Earth combined. As it pierced the upper atmosphere, friction ignited the air around it, encasing it in a blinding plasma sheath. To any creature that happened to look up, it would have appeared as a new, terrifyingly bright star, growing larger and more brilliant with each passing second. It was not an omen or a warning. It was a physical certainty, a final, catastrophic punctuation mark at the end of an entire geological era. The world below had only moments left. The impact was instantaneous and absolute. The asteroid struck a shallow sea off the coast of the Yucatan Peninsula, vaporizing on contact. In a fraction of a second, it displaced 100 cubic kilometers of the Earth's crust, blasting a transient crater over 180 kilometers wide and 20 kilometers deep. The energy released was astronomical, 1 billion times more powerful than the atomic bomb at Hiroshima. The initial flash of thermal radiation would have incinerated any life within a 1,000-kilometer radius. This was followed by a titanic shock wave, an air blast that flattened forests for thousands of kilometers more, and a series of mega tsunamis, some over 100 meters high, that scoured coastlines around the globe. Trillions of tons of superheated rock, ash, and vapor were ejected high above the atmosphere, some of it reaching escape velocity and leaving Earth entirely. The rest began to fall back, a fiery rain of molten blast spherules that heated the air to oven-like temperatures across the entire planet, igniting global wildfires. The day the world caught fire had begun. What followed the fire was a profound and lasting darkness. The vast quantities of pulverized rock, soot from the global wildfires, and sulfur compounds blasted into the stratosphere formed a thick, impenetrable shroud around the planet. This dense cloud blocked the sun's light, plunging the Earth into a state of perpetual twilight that would last for months, perhaps even years. This was the impact winter. Global temperatures plummeted, dropping by as much as 25 degrees Celsius. Without sunlight, photosynthesis ceased on a planetary scale. The phytoplankton in the oceans, the foundation of the marine food web, died off. On land, plants withered and died in the unrelenting cold and dark. For the dinosaurs, this was the ultimate catastrophe. The herbivores, creatures that consumed tons of vegetation each day, found their food source had vanished almost overnight. Starvation became the primary killer. For the great carnivores, like Tyrannosaurus, the extinction of their prey sealed their own fate. The intricate food web, built over millions of years, had been severed at its base. The reign of the giants was ending not with a roar, but with a descent into cold, silent starvation. Why did the great dinosaurs perish while others survived? The answer lies in the very traits that made them so successful. Their enormous size was now a fatal liability. A large, warm-blooded animal has a massive metabolism, requiring a constant, huge intake of food. When the plants died, the multi-ton herbivores that depended on them were the first to go. Their predators, equally large and specialized, soon followed. Their reproductive strategies were also a disadvantage. Most large dinosaurs likely took years to reach sexual maturity, and laid clutches of eggs that required long incubation periods. In a rapidly collapsing world, this slow life cycle was no match for the swift and brutal environmental change. They were specialists in a world that suddenly demanded generalists. The fossil record tells this story with chilling clarity. In the layers of rock below the impact boundary, we see a rich diversity of large dinosaur fossils. In the layers directly above it, they are simply gone. This great dying acted as a planetary filter, ruthlessly culling any species that was too large, too specialized, or too slow to reproduce. But life, in its relentless tenacity, found a way. The survivors of the apocalypse were almost universally small, weighing less than 25 kilograms. Among them were our own distant mammalian ancestors, but also a very special lineage of dinosaurs. These were the Maniraptorans, small, bipedal carnivores and omnivores that were, in essence, proto-birds. Their small size was their greatest asset. A smaller body requires far less food to survive and can hide from the harsh conditions in burrows, rock crevices, or hollow logs. Many possessed a crucial adaptation their larger cousins lacked: a full coat of complex insulating feathers. This wasn't for flight, but for warmth, a critical advantage in the freezing impact winter. Furthermore, their diet was far more flexible. They didn't rely on large prey or fresh vegetation. Instead, they could subsist on the detritus of a ruined world: insects, worms, seeds, and carrion. Seeds, in particular, were a vital food source, a pantry of stored solar energy that could lie dormant in the soil for years, waiting for the sun to return. These feathered dragons were built for survival. As the dust slowly settled and the sun's rays once again touched the Earth's surface, the planet began a long, slow recovery. It was a profoundly different world, an empty stage scrubbed clean of its former stars. The niches once occupied by the Titans were now vacant. This was the opportunity the survivors had been waiting for. For the small feathered dinosaurs that had weathered the storm, this new world was a blank canvas. With the competition gone, they began to diversify at an explosive rate. Feathers, once primarily for insulation, were co-opted for display and, ultimately, for powered flight. The descendants of these tough little survivors evolved into the first true birds. They conquered the skies their pterosaur predecessors had abandoned, spreading to every continent and diversifying into the more than 10,000 species we see today. From the eagle soaring on thermal updrafts to the hummingbird hovering at a flower, every bird is a living dinosaur, a direct link to the Cretaceous world. They are a testament not to the fragility of life, but to its incredible resilience. A feathered legacy of the dragons that survived the day the world changed forever. Our journey through the Mesozoic has reached its cataclysmic end. The reign of the giant dinosaurs, an epoch of unparalleled scale and power, was concluded not by a slow decline, but by a cosmic hammer blow. An asteroid 6 miles wide struck the Earth, unleashing a force 1 billion times that of an atomic bomb. The immediate aftermath was apocalyptic. Skies turned to fire, then to an impenetrable darkness as dust and soot choked the atmosphere, plunging the world into a nuclear winter that would last for years. Photosynthesis failed, food chains collapsed from the bottom up, and the giants, with their voracious appetites, were the first to fall. For 99% of all life on Earth, this was the final chapter. But extinction is not an absolute. It is a filter. And in the shadow of this global catastrophe, a few remarkable lineages clung to life. Among them were the smallest of the dinosaurs, creatures that bore a revolutionary adaptation: feathers. They had already taken to the skies, or were well on their way. Their small size, their warm-blooded metabolism, and their varied diets of seeds, insects, and carrion allowed them to weather the storm in a way their larger relatives could not. They were the meek, poised to inherit a shattered Earth. From the ashes of the Cretaceous, the Cenozoic era dawned. For the avian dinosaurs, it was a world of opportunity. The skies were empty of pterosaurs, the forests silent, the niches once occupied by their colossal kin now vacant. This was their moment, and they seized it with an evolutionary explosion. In the first few million years, they rapidly diversified, becoming the ancestors of all modern bird groups. The fossil record of this crucial transition is frustratingly sparse, a ghost lineage that paleontologists are painstakingly piecing together fragment by precious fragment. Yet the clues we have are spectacular. In the oceans, some abandon the sky entirely. Creatures like Waimanu, an early penguin from Paleocene New Zealand, developed dense bones and paddle-like wings, becoming expert divers. They were pioneers, retrading the air for the sea, demonstrating the incredible adaptability that had become the hallmark of the dinosaurian survivors. They were no longer just occupying the world, they were conquering new realms, laying the foundation for a new dynasty, one that would spread to every continent and every ocean on the planet. While many avian dinosaurs took to the trees, the seas, and the skies, some evolutionary echoes of their predatory ancestors re-emerged on the ground. For millions of years, in the isolation of South America, a group known as the Pterosaurs, or terror birds, reclaimed the title of apex predator. These were not the fleet-footed raptors of the Cretaceous, but something altogether more formidable. Standing up to 10 feet tall, Kelenken was a bipedal hunter built for power and speed. Its wings, useless for flight, were armed with sharp claws, but its true weapon was its head, a skull larger than that of a horse, tipped with a massive, brutally hooked beak. They were the dominant carnivores of their environment, a stunning example of convergent evolution. The theropod blueprint for a terrestrial superpredator, it turned out, was still viable. The terror birds were a bold statement. The ground, once shaken by the tread of Tyrannosaurus, now trembled once more under the feet of its distant, feathered cousins. They were a reminder that the heart of a hunter still beat within the chest of the dinosaur lineage. The story of this incredible survival and diversification is not one of conjecture. It is written in stone. The fossil evidence connecting non-avian dinosaurs to birds is now so overwhelming, so detailed, that it stands as one of the clearest evolutionary transitions known to science. We no longer have to guess at the texture or function of their feathers. We have found them preserved with microscopic detail, even revealing the melanosomes, pigment cells that allow us to reconstruct their original colors. The link is far more than skin deep. It is in the very architecture of their skeletons. The furcula, or wishbone, once thought unique to birds, has been found in numerous theropods, including Velociraptor and Tyrannosaurus. Their bones were hollow and lightweight, filled with air sacs connected to their respiratory system, a sophisticated feature that made them more efficient and paved the way for flight. Fossils of brooding dinosaurs, like Pseudopodi, found sitting on their nests in a posture identical to modern birds, provide a poignant, fossilized behavior, a snapshot of parental care that has endured for over 75 million years. Every new discovery adds another verse to this epic, strengthening a bond that time itself could not break. The journey into the air was not a single leap, but a gradual ascent, refined over millions of years. For early Maniraptorans, feathered arms that may have started as display structures or brooding aids became instruments for powered flight. We can trace this refinement in the fossil record. We see the shoulder joint reorienting, allowing for the powerful up and down flapping motion essential for flight, a motion absent in their earlier ancestors. We see the fusion of tail vertebrae into a pygostyle, an anchor point for a fan of tail feathers used for steering and braking with remarkable precision. We even see the appearance of the alula, a small feathered digit on the leading edge of the wing, which birds still use today to prevent stalling during slow flight and landing. And with the evolution of flight came the evolution of sound. The development of a syrinx, the unique avian voice box, would have transformed the soundscape of the Mesozoic. The world of the feathered dragons was likely not just a cacophony of roars and hisses, but a growing chorus of complex calls, chirps, and perhaps even the earliest forms of song. The soundtrack to an evolutionary revolution. The line that connects the ancient past to the living present is direct and unbroken. This is not a relationship of distant cousins, but of direct descendants. To see a dinosaur today, you don't need a time machine. You need only look out your window. Observe the foot of a chicken scratching in the dirt. Its 3 forward-facing toes and a smaller one in the back is the classic theropod arrangement. See how its leg bends, not at a knee, but at an ankle, just as a velociraptor's did. Watch an eagle descend upon its prey, its feet outstretched, its talons ready. It is a mirror image of the killing claw of a Deinonychus. The link is even encoded in their genome. Scientists have found that by suppressing certain modern bird genes, they can reactivate dormant ancestral traits from their dinosaur past, causing chicken embryos to develop teeth and snouts instead of beaks. These are not modifications, they are awakenings of a genetic memory. The bird is not like a dinosaur. A bird, in the most literal biological sense, is a dinosaur. They are a single, continuous, ever-evolving branch on the tree of life. So, the reign of the flying dinosaurs never truly ended. It merely changed form. It adapted, it endured, and it conquered the world anew. From the terrifying hunters of the Cretaceous plains to the iridescent hummingbird hovering at a flower, the thread of life is continuous. They survived the apocalypse that claimed T-Rex and Triceratops. They diversified into over 10,000 species, inhabiting every environment on Earth, from the frozen poles to the most arid deserts. They are the most successful and varied group of terrestrial vertebrates in the planet's history. Every dawn chorus is a symphony played by dinosaurs. Every soaring falcon is a testament to their mastery of the air. The legacy of the feathered dragons is not a relic of a lost world, confined to museums and fossil beds. It is a living, breathing, and flying reality. We have been searching for them in the deep past, but they have been here all along, hidden in plain sight. They are the dinosaurs among us.